Hello, welcome. Um, just to know a little bit, who was there yesterday for Emmanuel's keynote about Cloud Native? Okay, almost everyone. That's good. So my name is Clément Escoffier. I'm working at Red Hat. I'm architect / software engineer there. And today I'm going to talk about Quarkus and how to build reactive application and reactive systems with Quarkus without really having to handle the complexity behind this. So first thing is Quarkus. Quarkus is a new framework, a new Java framework to build cloud native applications like microservices or serverless. And the idea behind Quarkus is to move most of the work that is currently done at runtime by frameworks at build time. Thanks to this, we can reduce the memory usage, the startup time of your application, well, by around 20% in JVM mode, and if you really want to go at the end of the spectrum, by probably 100% in native mode. We are going to see these numbers in action. So, Quarkus has been released publicly in February, and we are now moving towards the 1.0 version. So we have a very, very fast pace in terms of development, and we are releasing every week. So right now I'm using the version 0.25, and this presentation and the demo I'm going to show you is going to be updated tonight because we are releasing today 0.26. So well, it should not break anything normally, but yeah, that just to let you know that if you want to replay it, you may want to update too. So Quarkus is based on 4 pillars. The first one in developer joy, a pretty awesome hot reload. You are inside your IDE, you code, you go to your browser, you refresh, you get your changes. If you made any mistakes, it's going to be reported, and we are going to see this. Then we have this subtitle, or this tagline, Subatomic, Supersonic, Java. Pretty fast, pretty small, and Java. The third one, about libraries and standards, is actually quite fun because when we released the first public version in February, a few days later, a recruiter was looking for people with 5 years of experience with Quarkus. Well, actually, he was not completely wrong because you mostly already have 5 years of experience with Quarkus. Who is using Java? Okay. Who is using JAX-RS? Who is using Spring? Who is using Camel? Vertex? Ah, quite some. If you, well, have used one of these technology, you already have experience with Quarkus. So you probably already have 5 years of experience with Quarkus. But today, in this session, we are going to look at this one, how we unify imperative and reactive. And that's one of the core pillars of Quarkus. So the thing is, yeah, well, reactive, come on, I Googled it, and what a mess. Seriously? There is hundreds of pages that talk about reactive, but no one is actually referencing the other one. It's like different things, and behind reactive you may have actually different stuff. And that's actually true. Well, a few years ago, TypeSafe, no Lightband, have released something called the Reactive Manifesto, which define reactive systems. Reactive systems are an architectural style for distributed systems where we use messages as a main way to interact. Because we use asynchronous messages, we need a way to write asynchronous code. And here, we have several approaches for this. We can use fibers, well, when Loom will be released, or actors, or callbacks with event spreadsheets. Do we have any manager here? Cool, I like your conference, Antonio. Well, or you can use reactive programming. When using reactive programming, you are going to use new construct, and the main construct is data flow. So you have pipes in which you have data inside this. When you have data flow, you quickly have an issue if you have a fast producer and a slow consumer. because you will overload your consumers. So for this, you need some kind of back pressure, some kind of flow control. This is reactive streams. And reactive streams give you an asynchronous and unblocking flow control for your reactive programming model. Obviously, reactive streams looks simple, but it's hell of a mess to implement. The TCK is very, very strict, but it gets some, well, traction. It's actually included in the JDK 9 under the name flow, so we will see more reactive streams very, very soon. But you don't want to use reactive streams by yourself. You don't really want to use back pressure by yourself. You want a library that hides that for you, and this is what we call reactive extension. And behind reactive extension, we have Reactive Java 2, and the next to be Reactive Java 3 and Reactor, which implement reactive streams and reactive programming. So if you use these libraries, you're good. However, how these libraries relate to the beginning of my story? Well, let's go back to the roots. So I'm a former academic, and well, like all academics, when we don't know something, we don't go to Stack Overflow, that's developer. We look inside a Oxford Dictionary. And when we look at reactive in the Oxford Dictionary, you get this page. It says that reactive means showing a response to a stimulus. That's good. The second definition is actually very interesting too. It says that you are going to react to a situation rather than controlling it. This is actually key in the reactive approach. If we apply this definition to software, we can make a definition. And that will say that a reactive software is an application reacting to stimuli like messages, failures, events. But all those stimuli, you don't control them. The application don't control them. Well, and then you say, that's not really true, right? And you're absolutely right. Reactive is not new. It existed long time before the Reactive Manifesto and so on, because we call that event-driven. And we had event-driven forever. It's the roots of computers. So everything is event-driven, more or less. When you do a keystrokes, you expect that at some point it's on your screen, right? So reactive is kind of event-driven. So it's like you have your applications that will get event, messages, failures, keystrokes, signals, whatever. All the stuff are outside of the not in control by the application. But reactive brings a different way to deal with this. Because we need to efficiently use the resources, we need to build better system. So to build this, in the reactive world, we try to build highly concurrent systems. For this, we use non-blocking I/O. That's the key element here. Everything, all the messages that you will get will use some non-blocking technologies. So you need to be aware of this because you cannot really use any thread affinity. We are going back to that in a moment. Then on top of this, we are going to use reactive streams because that's a stream of events, so you need some back pressure protocol, and reactive programming because, well, you want to code against this. While if you believe that you can handle all your logic by doing, if I get this event, I do this, fine, you don't need reactive programming, just need a callback. If you need to do things, well, give me the last 10 events and compute something out of this. Then it's much more complicated to do that with callbacks because you need cache and stuff like that. And when you have cache, you have another issue. So one of the ideas behind the reactive movement is to use a non-blocking I/O. Generally, it's Netty. Everybody is using Netty these days in Java. Then a reactive framework that will make Netty a little bit more affordable for the bare developer, because Netty, sometimes it's funny. And then the application code, I can use any kind of reactive model like fibers or RX or whatever. One of the core elements here is that we are going to use one thread to handle n concurrent requests, which is quite different from what you do generally in Java. The thing is, you don't want to limit yourself to one application. Well, this conference is named Vox Microservices, right? So you are building a set of services, and you want to apply event-driven to a set of services and not to a single service. And while doing this, it's actually quite fun, and it introduces new concepts. Because what you want to do is making this better, not only this element. So here comes reactive systems. Reactive systems is an architectural style to build better distributed systems that fit very well this microservices world, because the idea is to keep handling the request even when you are facing failure or even on fluctuating load. So basically, reactive means two things. On one side, build concurrent application using non-blocking I/O, reactive programming, reactive streams, and on the other side, build better systems using reactive systems. Okay, so we have these two facets that looks a little bit weird. There is some relation between that, but how does that look like in reality? So first, let's look at reactive systems. Reactive systems are based on 4 pillars, those ones. The first one is asynchronous message passing. All our microservices are going to exchange messages. By doing this, you are going to send messages to a virtual address, and because it's sent to a virtual address, you can have 1 to n subscriber behind it, depending on your load. So that gives you elasticity. Simple. On the other side, we have resilience. Depending on your message model or your message middleware, you can have things like acknowledgement, or if you have several subscribers and one die, another one can keep up and get the work done. So by having these, we can actually handle the requests, the messages, the events, even under fluctuating load with this elasticity pattern, or when facing failures with those resilience pattern. So we become responsive. And that's pretty nice, because responsive means that we will continue handling the request, and the users, your users, will be much more happy than getting saying something like, yeah, we're going to handle your request, than 500 errors, I'm on strike, or something like this. Anyway, one key element here is this, asynchronous message passing. And if there is one thing to remember from this talk, is this. Asynchronous, rare asynchrony, is not achieved by multi-threading. A lot of libraries claim to be asynchronous, and the only thing they do is just offloading the work to another thread pool. That's not really asynchronous. Asynchronous, if you really want to understand it and use it right, means never block. And here, let's explain it. Well, who use containers? Well, not so much. I would expect more than this. Even in dev mode, are you not starting on databases or anything in containers? Well, as a developer, I generally use containers because I have 2 systems listening on the same port, and that's a nice way to deal with this issue. But anyway, when you package your application inside the containers, well, it may work. You may take any application and get it in a container. Well, it's a Linux stuff, so as soon as it works on Linux, it will work. Except that it's actually not that right. Containers are not about isolation. Containers are about increasing the deployment density, which means that when you are deploying inside containers, somewhere in the cloud, there is poor CPUs and memories. We don't know where, but there is somewhere a farm of CPUs. The thing is, they are shared. Meaning that if you have those containers here, they are all sharing those 4 CPU here. If one of our application is getting or is taking a lot of CPU, a lot of memory, well, the other containers will get less. And one of the key aspects in this is the number of threads. One thread costs memory, around 1 megabyte. Sometimes a little bit more, depending on the operating system, depending on many things, but generally it's 1 megabyte. In traditional Java, your level of concurrency, which means the number of requests you can handle at the same time, is associated to the number of threads you have. So, for example, if you want to handle 100 requests at the same time, you need 100 threads. So, 100 megabytes of memory. So, that costs a lot of memory. And there is a hidden cost behind threads. More threads you have, more time you are going to spend doing context switching. And actually, I read last week that context switching is around 56 nanoseconds. You say, that's nothing. Well, how many context switches are you going to do? And this time is really not productive. It's just memory flipping and restoring everything. So, you don't really want to use CPU cycles like this. And you can say, well, but no problem. I can use memory limits or constraints, and everything will be fine. Ha! What happens when a container reaches limits? It gets killed. 137 if you are doing Java. That means, okay, memory exceeded, done. You're dead. Not really responsive, right? You don't want this. So we need to think about a new model where we are going to efficiently use the resources and reduce the number of threads. And by using non-blocking I/O, by using all the things I just explained, we can achieve this. So what's the journey? How do we go from synchronous HTTP? Who is using HTTP between microservices? Yeah, almost everybody. So how we can move from this to asynchronous messages and get something a little bit more resilient, a little bit more responsive. So the first thing to understand is that HTTP is introducing strong coupling. And the fact is, microservices were about loose coupling. Was about I'm able to update any of these at any time, except that there is some temporal coupling here, which means that if I'm too far. No? Oh, yeah. If one of our microservices dies, because there is temporal coupling, the callers will get an error. And the caller of this one will get an error. And the caller of this one will get an error too, until you get a sad panda, which is your customer, that will get an error. And you don't want this. So this idea of temporal coupling is actually key in microservices. And that's why HTTP is not really great for this. I agree, it's convenient, but not necessarily what you're looking for. You can say, well, no problem, I get your back. Circuit breakers all over the place. Yeah! Who use circuit breakers? Who love tuning circuit breakers? So you missed half of the fun, right? Circuit breakers are this idea that I'm going to monitor one interaction, and if something failed too often, I'm going to stop that and call a fallback. Fine. I have a bank account. I'm going to check how much money I have on my bank account. Ah, too bad, I get a fallback. What does it say? 42? That doesn't work, right? So sometimes fallback doesn't work. The other thing is that behind each circuit breakers, you need to anticipate the concurrency of the service you are going to call. How do you know that? How can you predict the future? Because maybe right now you have one instance of this microservice. Maybe in a few minutes you will have 5 of them. So all the tunings you'd made is off. So it's very tricky, and the only thing to do that would be to have active monitoring and reconfiguring your circuit breakers at runtime and so on, which will be even more fun. And actually, if you think about this, you say, well, okay, so if this is not the right solution, what can we use? Messaging. 25 years of experience. It's come from the 60s, so even more than 25 years. We know how to operate that, and it works very, very well. We will use non-blocking message passing, AMQP, Kafka, whatever, Pulsar. We have elasticity pattern because of the virtual addresses. We have resilience pattern. Those are all, the only issue with this is that, well, I did messaging one during the Java EE era with GMS, or in the Corba era, because I had some messaging too, and that was a mess. And I agree with you. That's why we try to take another approach in Quarkus. The other thing behind messaging is that there is many, many patterns that we cannot achieve with HTTP, like data streaming. You have a lot of messages, you want to compute things on the fly with event sourcing and things like this. So we need to be able to handle message streams. Messaging doesn't mean that you cannot handle request reply. Depending on your protocol, you can use request reply. And the last one, publish subscribe. Everybody knows publish subscribe. But try to implement it with HTTP. Then you don't have an issue with temporal coupling. You have a lot bigger issue because everything gets coupled to this. HTTP is not made for publish subscribe, while messaging is made for publish subscribe. You say, well, but why do we need these patterns? Because a few years ago, we were using data at rest, and now we are using data in motions. We have a lot of data that get collected at any time, and that get processed on the fly until it reaches a data lake. And I attended a talk this morning where they say, well, data lake is where the data dies, and I agree with this, but anyway, It's what we are building these days. So, okay, but what about Quarkus here? How does it fit in this picture? Well, Quarkus has a reactive engine, and that's a key element. Everything you will do on Quarkus is actually going to be based on Eclipse Vertex, which relies on NETI. So messages, HTTP, events, everything goes through this reactive engine. And on top of this, it will route your request or message depending on what the route you declared on your application. So it can go to servlets with Undertow, to REST-easy for JAX-RS or Spring MVC. Reactive messaging, we are going to look at this in a few minutes. Reactive routes, which are a router approach for HTTP, and more, like integration pattern with Camel, or reactive data access, which give you a non-blocking approach to interact with your databases. So if we didn't have this, well, we would be able to do this, but this one would be off the chart, not possible to implement them. So it's really important to have this pipeline here, this thing. So how does that work? So Quarkus will be able to handle almost any interaction styles you want. It goes from HTTP, messaging, streamings, and so on. We have non-blocking I/O, because Vertex is non-blocking, which will get to your HTTP request, route that through Quarkus, call, I don't know, let's say a JAX-RS endpoint, Spring controller, whatever. Then go back there, send a message to something else using a messaging middleware, and another application which doesn't use HTTP, but just gets some messaging and streaming, gets the application, and so on and so on and so on. So there again, how does that work? How do we avoid things like GNDI or GMS or all the technology we loved in the 90s, which was almost 30 years ago, right? So yes, we're actually going to use microprofile reactive messaging. Microprofile reactive messaging is the specs that we released in September-ish, I guess. Check the date, I don't remember. And this spec is actually going to provide a much simpler model for you to use messages. It's actually use 3 annotations. That should be fine, right? 3 annotation, you can handle that? Let's see. Okay, we are going to use a demo for this. So I went, just after lunch, sorry Antonio for this, I went to the coffee over there, just down the road, because I really need an espresso, you know, black, strong, short coffee. And it was really a traditional coffee where I had to queue, and the bartender was serving 1 coffee at a time, which is fine generally, but yeah, I had to wait a few minutes to get my coffee. While we have this new generation of coffee shops. This new generation of coffee shops is actually a little bit different, where you go to the bar, you go to the counter, you ask for what you want, they get your name, they misspell it, for sure. Well, my name is Clément, imagine that. Now I say Jim everywhere, or John. I can't, yeah, this doesn't work. And then they say, okay, wait over there, and when it will be ready, you will be called. This is much more reactive, because here we can have a coffee shops where as soon as you order your coffee and you paid, then it will send messages to a Kafka topic. 2 messages actually, one for your orders that will be read by the barista, and one for the queue where you will know where your beverage will be ready. And then the barista over there will get the orders, prepare the beverage, and send another message to the queue saying, well, your drinks is ready. So one thing to keep in mind here is that I'm using Kafka because, well, we want to be cool, right? And actually, in the past 2 days, we had a lot of Kafka things. But the code I'm going to write has not any dependency on Kafka. And you can use MQP, you can use RabbitMQ, you can use MQTT, you can use whatever messaging protocol you imagine. So let's see how it works. So the first thing to understand is what the issue is HTTP and synchronous. And be careful, I'm not kidding about coffee. I really need a lot of coffee. So if there is a lot of customers, then the concurrency of my bartender is going to be limited by the number of threads, which means that I need to scale up the number of baristas or require some kind of load balancer to handle this. So in that case, I may get cold coffee or no coffee. I don't know which one is worse, actually. but it doesn't sound good to me. If we have a failing barista, then it's even worse. You paid and you won't get your coffee. That's terrible. Or if the barista is a little bit tired and so on, then, well, you may get some cold coffee. And you don't really want this. So HTTP here doesn't really work well. So let's demonstrate this. Okay, let's switch to some code. Okay. Can you read the code? Is that large enough? Let's do something like this. So I have these pages, oops, over there. Let's increase that too. Which is a little bit my coffee shop. So yeah, it's still there. So Antonio, yeah, well, misspelled, will get a chai, because fancy. And right now it's using HTTP, and well, fine. Tom, the barista, has prepared a chai tea to my friend Antionia. Almost there. The issue with this is that if at some point my HTTP service is done, then if I want another one, like a hot chocolate, you like hot chocolate, right? Boom! Doesn't work anymore. Because the service I'm calling is not there. So I get this error here, which makes sense, right? You can't call coffee. You can't call the barista if there is no barista here. Okay, so we need to switch this to messaging. Is what I'm going to do here. So that was my code of my coffee shop. I was using a REST client, so microprofile REST client to call my barista service using HTTP, and that was the call that we were making. So right now, from this point, I'm going to switch to a reactive world. But here I'm in a JAX RS endpoint. So I need to have access to streams, to stream of messages or events. I need to feed those streams. So I'm going to use an annotation named channels and an object called emitter. And because I want to keep things simple, I'm going to send string, and that one is named orders. I need a second one, remember the Q one, that I will name Q. And here I need to change Q here. So first annotation, channel. Then here, in this method here, I need to do and send messages. So the first thing I will do is call process order, which means that I'm going to pay processed. Okay, and then I'm going to send my messages. So I will get Q dot send. I need a preparation state as a serialized one, which is just a JSON object. Here it needs to be processed. And I'm going to do the same thing with the orders one, which will be read by our barista. And here, just this. And now I need to return processed. That's all. Here, in this 4 line of code, I have sent 2 messages, 2 channels. Nice, but I didn't say anything about Kafka yet. Don't worry, we are going to come to that in a few minutes. But let's see if it works. So this was started here in dev mode using Quarkus. So let's see if that works. And now I'm going to try to get a coffee. So my name is Jim, as you know. And I'm going to get some latte and place some order. Here, it's in queue. Oh, I forgot something, right? Yeah, we don't have any barista. But at least the orders, oh no, I forgot to stop it. So we actually had a barista, which his name is Julie, that prepared my latte. It's pretty nice, right? So let's have a look at this barista. How does it works? So this barista is using 2 other annotation, incoming and ongoing. So this is another microservice running in its own process, and it's telling that is interested in messages from the channel orders and is going to write things to a channel named Q. All done. Channels, incoming, ongoing. You're good with this. Everything else is just decoration. Here, this method here is getting some orders here. So because I didn't want to write my own serializer, I just sent some JSON. So I'm rebuilding the JSON object here. And because preparing coffee takes time, I'm using some asynchronous method. Reactive messaging is providing more than 30 different signatures. So it can be synchronous, it can be asynchronous, it can use streams, it can use whatever you want. Eric Java 2, we got your back covered. So look at the spec or the small right documentation, which lists all the different variants, and pretty sure you will find the one you need. Okay, so that's nice. We got this, but what about not having a barista? So Julie was there. I'm going to stop Julie, and I'm going to ask for another coffee. Many coffee, because I need a lot of coffee. Well, nothing is going to happen, right? Because we don't have any barista. In an HTTP world, we will have failed immediately, in the sense that, well, the barista is not there, 500, boom, go back later. But here, the orders are kept. And as soon as the second barista, or even Julie, if she comes back, we will, it will handle the load and start processing the different messages. That's what we should get here. So Tom already handled 2, 3, 4, 5. So you may wonder about ordering here. And that's actually Kafka specific. So depending on your channels or the implementation of the connector, you may want to look at it in details to be sure that your ordering is right and so on. Okay. Tom did a pretty good job. I got all my lattes now. So the main difference with HTTP here is that, well, even if the service is not there, all the request has been durably stored in a Kafka topics, and then as soon as the barista is there, it will be processed. So what about load balancing, the elasticity one? I'm going to restart Julie. So we will have Tom and Julie at the same time. And I'm going to be named John now and get some espresso. And I'm going to hammer this. And we will see. And now we see some kind of load balancing because both Tom and Julie are actually preparing my coffee. So what we see here is that elasticity is actually very easy to achieve here. I just restarted my microservices like I would have done a scale up. Done. No need for any load balancers or whatever. Messaging is covering that for me. And then you say, yeah, okay, but that was very Kafka specific. So where is the Kafka code? Well, let's have a look. Not this one, yeah, this one. Here it is. That's my coffee shop service, and that's how it's configured. So the first thing you say is that my channel orders is actually using the small white Kafka connector. There is some other connector for Kafka for this spec, so I'm using the one I've built myself, because, well, that's my favorite one, obviously. And then you say what kind of serialization you need. And then you can configure your consumer or your producer using any of the hundreds of the attributes from the Kafka specification. So it just uses the internal Kafka things. Same thing for the incoming one, for the beverages, which is actually the one used by the dashboard, where you can configure the topic if it doesn't fit if it doesn't match the channels, and the deserializer, and so on. 3 annotations, 3 lines of properties. That's all you need. And here we have built, in a few lines, a reactive systems. It uses messages. We have seen that it can scale up and down. And we have seen that even if one of our barista failed, he will recover. He will handle, well, keep the order pending. And as soon as someone is ready to handle it, do it. So let's go back here and summarize what we just did. So we have seen the issue with HTTP. If the service is not there, boom, doesn't work. we have seen this first channel annotation, which combined with the emitter, let you emit messages to a channel. This channel can use Kafka, can use MQP, can use an internal in-memory channel or whatever. You don't care. And now you can say, well, but I actually like Kafka and I really want to configure, I don't know, partitioning or things like this, or the key. You can also emit a Kafka messages. And if you emit a Kafka message, which is one of the classes that is provided, then you will be able to configure all the aspects of Kafka. But in that case, your code is not portable from one messaging technology to another one. That's why we try to avoid that. And actually, we are the feedback we have on this is that nobody cares and they just want this. Then we have seen on the other side how we can process message on the fly. Remember that I in motion using @incoming and @ongoing. 3 annotations. We're done. We have seen this, how it works in actions, and then we have seen the board that was pushing the messages to the browsers. So I've used SSC. I could have used WebSockets, I could have used, well, yeah, probably only WebSockets and SSC for the browsers, or SockJS. But here I'm using SSC, and actually what I'm doing here is that I'm reusing the channels qualifier to inject the beverage channels as a publisher. And then you say, what's a publisher? A publisher is one of those reactive streams types, which means it's a stream of data. Here it's a stream of string. And then I'm taking these reactive streams and just passing that or returning that from my JAX server endpoint, saying that it's an SSC a connection, and it will just, every time it gets some messages, write that down to the SSC, and my browser is going to get that and display it. I'm not going to show you my amazing JavaScript page because it's terrible. And if there is any JavaScript developer here, I would be ashamed. So that's what we have seen here. How it's configured, okay? But also that even if we don't have any barista, or if one of the barista fails, that the orders are still there. So that means that even if I try to access my bank account, or do a transaction or something like this, it won't be lost. It will just say, okay, it will be done later, but it will be done. And that's actually key between microservices, because we are breaking this temporal coupling that is actually killing all the microservices we do. And if we actually have HTTP between your microservices, think about whether you have built a microservice system or just a distributed monolith. And you know what? Distributed monoliths are slower than monoliths. Yeah, network. Amazing, right? So you need to think about that. That it may not be what you want, and with these technologies, well, relatively simple. We also have seen the load balancing, how it works. You can imagine if you are in Kubernetes or if you have using any orchestrator to automatically scale up and down based on the size of the queue. So that's very easy. Here I've deployed on my machine, but you can deploy that on OpenShift, write a small operator that look at the size of the orders and decide whether you need 1, 2, n baristas, and so on. So that's a few lines of code. Or you can just configure auto scaling too. That would work too. So, Quarkus, HTTP, messaging, streaming, all in one box. Hot reload, reactive, and imperative. So basically you can almost do anything from a CRUD application to an IoT gateway. Something that is very event intensive, something that is just traditional Java applications. It can manage that. And it goes even beyond this. We now have extensions, so Quarkus plugins that will let you do things like BPMN. So rules-based processing. We have Kafka stream support if you are really in the Kafka world. We have Camel support if you need to integrate with anything, even very old COBOL services and so on. It will work in Quarkus. One thing I didn't really mention is, okay, but what do I gain doing this? So remember Tom, our Tom barista here, it actually was compiled in native. So native is the second step of compilation that Quarkus allowed because it does a lot of those build time things. And Tom was compiled like this and started like this. So the first thing is the startup time. Oh, let's restart it. Oh no, because I want the resources. The startup time is probably around half a second or even less than half a second. Let's see, it's 0.035 seconds here. It might be too small to read that. How long does it, well, who is using Kafka here? How long does it take to start any processor or producer or consumers? 1, 2, 3 seconds? 2 seconds? 0.035 seconds. Let's look at the memory. Yeah, that was a kill. If I ask for the memory of Tom is using 54 megabytes, which is actually quite a lot, so that's probably something I want to check, because normally it's around 30, but as it's used the latest Quarkus, we may have some regression about that. 54 megabytes of resources, of RAM that is going to be used. If you do that on a regular Java process, it will be at least 200. Well, with this, I can put 4 times more applications than with regular Java. Think about it, 4 times. It's really a game changer here. It doesn't, and all reactive and imperative and so on. So you may wonder now, what about reactive streams? Because I mentioned that, I say back pressure and so on. Actually, reactive messaging, so the spec, is actually implementing publisher, processor, and subscriber for you. And is really building this reactive pipeline with all the back pressure supported. So when you do a channel or ongoing or a connector, that's publishers. When you use at incoming and at ongoing, that's a processor. Or if you just use channels with a publisher or incoming or a connector or a sync, then it's a subscriber. You can, if you really, really want, but you need to think about it twice, use those types directly inside the methods that are annotated with at incoming and at ongoing. But again, most of the time, it's not what you really want, and you don't really want to mess up with these types. But yeah, back pressure is handled for you, and for you, you have used 3 annotations, and that's all. All happens there. So, final slide, Quarkus. You can mix imperative, reactive, and this is only possible because at the core, it's all reactive, it's all non-blocking. And then we route the requests, the messages, depending on what you are calling. So for imperative, you can imagine CRUD or REST or CLI. CLI is coming, it's not really there yet in Quarkus, but yeah, we are working on this. For reactive, you can build data streaming application with Kafka streams or even reactive messaging for this, or reactive systems, because what we built here was a reactive systems. Isn't that much, much simpler than GNDI, GMS, and so on, or much simpler than any other technologies that we use to build such kind of better distributed system? Right? 3 annotation should be able to handle it. It even comes with Javadoc that I wrote with a lot of love. Believe me, it's like this. But yeah, that's all I have. Thank you very much. On the first slide, you had the link on actually on this slide X, and on the slide of the demo, you had the link to my GitHub repository where you can replay this demo. I'm going to tweet them very soon, so you should be able to access them today. And we have 1 minute for questions. Yes, one. Yeah, so if you want to handle ordering and well, actually keys in Kafka, yes, you need to send a Kafka messages and set the key inside of it. So you just send a Kafka message of key and the value, and then you will have your order working. one type of message. Yes, other types, the types that I cannot read are just discarded. So someone else is going to handle them because they won't be acknowledged. Was there? Yeah. Mm. So for servlets, you need to look at Quarkus HTTP, which is under the Quarkus organization. It's actually a complete implementation of servlets on top of reactive engines. And yes, to handle imperatives, sometimes we have a worker thread pool, but we share the same thread pool for all the different facets of Quarkus. So at least you tune them once, but yeah. So, but yeah, for servlets, it's a complete implementation. For WebSockets, it's almost that too. For REST-easy, we have still some work to do, but it's almost there, yeah. REST-easy is actually much bigger than Undertow. It's unbelievable. Yeah, there is a client side too, and things like this. It's blinking and it's red, so it probably means that I don't have time anymore. I will be around if you have any more questions. There is some stickers here, and if you do the workshop tomorrow, Antonio will be great. Thank you very much.